Central Limit Theorem is the second most important topic in statistics. So we already talked about the empirical rule, the 68, 95, and 99.7 rule associated with the normal distribution. So the central limit theorem is something of a concept that was introduced by statisticians for practical purposes. Because in the real world, your data will never map precisely to a specific distribution. And you can see in the three figures that I have placed that there is a discrepancy between the actual distribution and the shape that the data has created. So there's always a difference between them. Sometimes it is difficult to work out exactly which distribution is the best one to base our testing around it. So the central limit theorem is a statistical theory stating that if you take a sufficiently large sample size from a population with a finite level of variance, then the mean of all samples from the population will be roughly equal to the population mean. So this theorem is very useful and is applied in finance when analyzing a large collection of securities, for example, to estimate portfolio distributions and trade for returns, risk, and correlation. Here we have an example. Consider that there are 15 sections in class X, and each section has 50 students. Calculate the mean average score of the entire population of students in class X. Now, the standard approach will be to calculate the mean average. For example, add the individual scores achieved by all students in class X and divide the total score by the total number of students. However, what if the data in the total population is extremely large? For example, the population of the United States of America, or the population of people living in the United Kingdom, which is millions. So, is the standard way of calculating the mean average of the population the best one? Well, in these cases, it probably is not for practical purposes because of the large numbers. So in our example, calculating the mean average score of students in class X will be a tedious and time-consuming process. So, if there's an alternative approach that is less time-consuming and less tedious, this is something that we should consider. And answering the question, is there a less tedious, less time-consuming way? And the answer is yes. Select groups of students from the class at random. This will be referred to as a sample. So we have to collect several samples, each consisting of 30 students. And the number 30 is not random because earlier in the central limit theorem, we talk about if the sample size is large enough. And here we get to a specific figure. If the sample size is larger than 30, then we can calculate the mean average of each sample and we can calculate the mean average of the sample means. So the total average will be the approximate average score of all students that have been enrolled in class X. And the histogram of the sample mean scores of the students will closely resemble the bell-shaped curve of the normal distribution. So, in a nutshell, the Central Limit Theorem states that as the sample size gets large enough, i.e. greater than 30, then the sampling distribution becomes almost normal, regardless of the shape of the distribution of the original population of interest. In practice, if the distribution is skewed, for example, if it is asymmetrical, the sample size should be greater than 30 before the means can be assumed to be distributed normally. Otherwise, if in practice the approximation to the normal distribution is sufficiently good, then the sample size should be at least 20. And in this case, the underlying distribution is reasonably symmetrical. Then we can assume that the shape of the distribution will be almost normal without being too far off, from the reality. So what are the assumptions that we have to make for a skewed distribution? Samples must be independent of each other. No connection between the samples. Samples must be random. Samples in terms of size must be equal. And if the population is skewed or asymmetric, the samples should have sufficiently large, for example, a minimum of 30 samples. Now, if we take a look at the illustration of the Central Limit Theorem for a skewed population of values, and you can see this in our figure. So panel A shows the population highly skewed right and truncated at 0. And panels B, C, and D show distributions, the mean of sample sizes of 15, 30, and 60 respectively. And as you can see, the larger the sample size, the closer we get to the shape of the normal distribution.